Okay, so today we're happy to have the Dickstein expert to tell us about relative symplectic cohomology pairs.
Thank you very much. Very much. It's a good pleasure for me to be here. Thank you very much. Today I'm going to talk about relative symplectic cohomology of pairs, and this talk is based on the joint work with Yaniv Ganor, Leonid, Polterovich, and Frol Zapolsky. So, my planning is to start with a short survey on singular cohomology, and then I'll move to relative symplectic cohomology that is defined by Varolgunes, and we generalized it for the case of relative symplectic cohomology of pairs. In order to get a new application to symplectic rigidity, we have to use all of this theory and define a tool called ideal valued quasi-measure, and it will help us to prove all the applications. Okay, so let's start. What is a singular cohomology? So singular cohomology is a functor from the category of topological spaces to abelian groups. X goes to Hx, and it has a standard model of chain level. So this is another functor, singular co-chain complex, takes topological spaces and give us chain complex. Also, X goes to C of X, and the singular cohomology of X equals to the homology, depending on how you call it, of the chain complex, co-chain complex. And from functoriality, we know that if we have a subset of X and A and subset B of A, then the restriction map from X to B equals to the restriction map from X to A and then to B. And how we can define singular cohomology of pairs? We defined it using kernels of restriction map. So the complex is defined to be the kernel of the restriction map from X to A, and then we take homology. Okay, so that is the definition of singular cohomology of pairs. And singular cohomology has several structures and properties. For instance, Meyer Vietoris, and in order to get Meyer Vietoris, we have define a notion of excisive couples. So a pair AB is called an excisive couple if the natural map from the chain complex, not co-chain, chain complex of X plus the chain complex of B, the map from this into the chain complex of the union is a quasi-isomorphism. So that means that it induces isomorphism in homology. So, but we get that a pair is an excisive couple if and only if it satisfies Meyer Vietoris. Also, we have cup product. So, cup product is defined for a couple, for pairs. So, it goes from the cohomology of X, A with itself to itself, to H of X, A. And for any pair of a subset, we can define a product of X, the cohomology of X, A with the cohomology of X, B, and it goes to the cohomology of X, the intersection. That happens in general. We use restriction map and then cup product. But in the case of excessive couple, we can upgrade it and get that the product goes to the pair X, the union. You can think about it like in the case of the Ham cohomology. If we have two differential forms, first vanishes on one set and the second vanishes on the other, then the wedge product vanishes on the union. So that is the picture. Okay, question about this? No, great. So relative symplectic cohomology, what is it? So given a closed symplectic manifold, Varolgunes defined a functor called relative symplectic cohomology from the category of compact subsets of M with respect to inclusions and the morphism, which is just the order, to lambda algebras. Lambda is the Novikov, the universal Novikov field, but it doesn't matter for this talk. And the product structure was defined by Togonog and Varolgunes. Okay, great. Also, satisfied that the relative symplectic cohomology of all of the manifold equals to the quantum cohomology as an algebra. So the product is the same like the product in the quantum product, and also the relative symplectic cohomology of the empty set is 0. Now, if we want to define relative symplectic cohomology of pairs, we have a model of cochains. So what we can do, Varolgunes also defined a model of cochains. How we defined it, let me sketch it. It's just a sketch, but the main idea is here. So given a compact subset, we can take a sequence of Hamiltonians, which are monotone, and on our set, they converges to 0, and outside of K, it converges to infinity. And then, given such a sequence, we can define the cochain complex of K, the symplectic cochain complex, to be the direct limit of the cochain complex, the Floer cochain complex of HI, and then we take a completion. What is the target of the purpose of this completion is to kill the periodic orbits that are far from K. So what remain the Morse critical points on K and periodic orbits on neighborhood of K, but the Floer trajectory can travel all of the manifold during all of the manifold. So we just as an ideal want to kill the periodic orbits outside of the manifold or outside of OK. And then the homology of this complex is relative symplectic cohomology. But this is not really well defined, but up to homotopy, since we can change the sequence HI. And also, this model has a restriction map that we can give them by continuation maps, and they are also defined up to homotopy and factorial only up to homotopy. So now the restriction map from M to B, if we compose it with the restriction from A to B, from M to A to B, it not equals to the restriction from M to B, but it's homotopy. There is a homotopy between them. So since everything is up to homotopy, we can use, in order to define the very notion of relative symplectic cohomology of pairs, we have to define a notion of homotopy kernel. So we used a model of homotopy kernel called Co-Con. So given a chain map from C to C prime, the Co-Con of F is the direct sum between C and C prime, but we have to do a shift degree by -1 to C prime. So this is yes, question.
You don't also deform the differential by F?
Yes, there is a different definition of the differential using F, and yes.
So right. Just the shift of the cone by 1?
Yeah, but and the as a module, yes. And as a when we want to define differential, we have to take care of the map F. And in what means this is a homotopy kernel. It is an homotopy kernel since in the sense that if we compose, if we take from the projection from this model to C, and then we compose it with F, then what we get is a homotopy to zero. Is homotopic to zero. Thus, so after this definition, we can define the notion of relative symplectic cohomology of pairs. And first, we will define the complex. So the complex will be the co-con of the restriction map. This is a natural generalization. And people doing it in other cases of another theory of cohomology. So this is not a very new approach. And we define the cohomology of the pairs to be the homology of this complex. And okay, so maybe this is a good stuff, a good point for a question so far.
So,
yes.
So see the definition of the co-con.
Yes.
Where is F? F comes.
F is coming in the differential.
In the definition. So you didn't write. Okay.
Yes. Exactly. Now, also the relative symplectic cohomology has a version of Meyer-Vietoris, and for that we have to define an analog of excessive pair, of excessive couple. So there is an analog, algebraic analog called descent. So A and B satisfies Meyer-Vietoris if and only if they are in descent, but the definition doesn't important for this talk. So let me just tell you about a sufficient condition, which is important for us. So when a subset are in descent, when a subsets are in descent, so we can define the notion of Poisson commuting sets, commuting set. So we said that set A and B commute if there are Poisson commuting functions such that A and B are exactly the zero set, the zero sets of these functions. Okay, so examples. If in the case of sphere, if we have two disks with disjoint boundary, then they are commuting. But if there is an intersection, they are not. And it's held only in dimension 2. In higher dimension, they could intersect. The boundary could intersect. And what Varolgunes proved, he proved that if A and B commute, then they are in descent. So actually, we have Meyer-Vietoris sequence in the case of commuting sets. And actually, for me, this is the only case that I'm familiar with it.
So sorry, what's the definition of in descent?
So I didn't present it, and this is a kind of algebraic definition connected to a push out of some theorem. Okay, great. So descent and products. So in the case of singular cohomology, we know that there is the concept of cup product, and it is defined, and there is an upgrade case of it in case of excessive pairs. So also we defined a product on relative symplectic cohomology of pairs. Sorry, on the case of one set, it was defined by Ganor and Varolgunes. We defined it for pairs, and like this, the same case in the singular cohomology, we can define it from pairs of two sets, m comma k and m comma k prime, and it goes to m comma the intersection. But in the case of when k and prime are in descent, we can upgrade it and get a product from SH of m comma k times SH of m comma k prime to SH of m comma the union. The similar case like similarly like the case of the singular cohomology. And also we have the following commuting diagram that tell us what is the connection with the product of Topological Varolgunes. Okay. Questions? Okay. So we developed a theory and we want to prove some results. So what we can do, we defined a new tool called ideal valued quasi-measure, which is a symplectic analog of ideal valued measure due to Gromov. And I say a few words about it later. But for symplectic application, we need this object, ideal valued quasi-measure or IVQM. So what is the definition? We have compact symplectic manifold and graded skew commutative associative unital algebra. Okay, you can think about the cohomology of M or the quantum cohomology of M in the symplectic case. Then an AIVQM is an assignment that takes open sets of M and send them to graded ideal of A. And it satisfies several axioms. For instance, normalization, monotonicity. The main property is quasi-multiplicativity. It tells that if U and U prime commute, then the product of their measure is contained in the measure of the intersection. Also, we have an intersection property. It says that if U and U prime cover M, then the measure of the intersection equals to the intersection of the measures. And since we're in the symplectic world, we have invariants under a simp 0 and also vanishing. That means that if K is displaceable, then its complement has full measure and it has a neighborhood of measure 0. Here commuting, I define it for complex set, but we can define it also for open set by taking complements. That is the same definition. And two remarks. First, we can extend it for compact sets by taking intersections. And additionally, the standard definition has two more properties, but they are not so important for this talk. But in our paper, we proved another two axioms of properties of this object. The first is a kind of an additivity, and the second is a continuity with respect to increasing unions. Okay, let me give you an example. Examples are the main things in this talk. So on the sphere, with the standard symplectic form, normalized, and you can take any algebra, and when I'm saying algebra, I mean graded, skew symmetric, associative, unital algebra. And for any connected open set, we can define its measure in this example to be 0 if the set is contained in a disk of measure of area at most half, topological disk, and A in any other case. So in this picture, Y is a small disk, so its measure is 0, and A and X is a thin annulus that contains the equator, so its measure is A. On the right, you can see two such a thin annuli, but with small intersection. So the measure of the intersection is 0. So you can see that the product of the measure is not contained in the measure of the intersection, but this set do not commute, so it's not problem, it's a feature, it's a negative feature. Okay, also we have a general construction that uses relative symplectic cohomology. So let me show you the construction, present the construction. So for given a closed symplectic manifold, we can define its quantum cohomology IVQM, sorry, as follows. So take an open set, and we will define its measure to be the restriction, the kernel of the restriction map from M to the complement of U. So you can think about the elements of this idea like element with support in U in some sense, just as an intuition. And what we proved that this is a really IVQM over the quantum cohomology. Now here I'm a bit cheating since to give an IVQM that satisfies continuity, we have to do some regularization property process and take intersections and unions and something like that. But this is the heart of the construction. This formula. Okay, so we have to change it a little bit, but this is the heart and the main part of the construction. And the example from the last slide is give us the same IVQM for the case where A is the quantum cohomology. Okay. Let me show you some computational examples. So on the 2n torus with standard symplectic form, and we can take an integer k between 1 and n, and consider a quasi-tropic torus T for which all the first k coordinates are 0. So this is a quasi-tropic torus. And what we proved that its IVQM cohomology, quantum cohomology IVQM equals to the ideal that is generated by the wedge product of a DPI where I is between 1 and k. Okay, and here I wrote a singular cohomology since torus is an spherical manifold, so there are no holomorphic curves here. Also, we have a QNet formula, and it says that, so consider L, let L be an equator in the sphere. And what we showed that the IVQM over the product manifold M times S2 of the subset times the equator is contains the tensor product of the measure of K times the measure of L, which is just the quantum cohomology sphere. And if we can combine these two observations and get that the measure of the torus, is in particular non-zero, but we know that it contains the measure of the torus times the quantum cohomology of the sphere. Question?
So if I take two torus and I take a contractible curve.
Contractible.
On the two torus that's embedded, that's where on one half of it, the contractible part, it has half the area of the torus. What's the IVQM of this? Do you know?
Contractible. No.
So you're taking like a loop.
Yes.
I'm saying like just draw it around so that.
Your question is about the disk, actually.
No, my question is about the torus. I have
the torus.
I have
It's in the torus.
Yeah.
Yes.
Half area disk.
Yes. So the measure will be zero.
Okay.
The measure will be dark. Okay.
Very sad.
Yes, you're right.
That would have
Very,
been
very sad, but this is the situation. Yes. Actually, Max Sun and Varolgunes proved that if the IVQM is not zero, then the set is heavy. And in your example, the set is not heavy.
Really?
Yes.
It can't be displaced from itself, but I guess it's not heavy.
Yeah, but it's heavy is another definition that you use quasi-states. So yes, what you said is non-displaceable, but it is an open question if it is non-display stably non-displaceable. So it is an open
Okay,
question.
good, good. So you-
Okay. What is the connection to relative symplectic cohomology of So in our change definition, we define the IVQM of a set to be the kernel of the restriction map. And using the relative symplectic cohomology of pairs, we have an exact triangle. So here we have exactness. So here is the restriction map. Here is a projection from the map, not projection, from the relative symplectic cohomology of A, the complement of A. Then the IVQM of A equals to the image of this map. And I want to prove that if A and B commute, then the product of their measure is a subset of the measure of intersection. So let me prove it. So take two elements, one from tau of A and the second from tau of B. From exactness, we know that there are A prime and B prime such that A prime goes to A and B prime goes to B. This is from exactness. Now, from the Morgan rule, we know that SH of M comma, the union of the complements equals to SH of M comma complements of the intersection. Okay, and using our commutative square, we get that the product of A prime with B prime is a subset of SH of M comma the complement of the intersection. And thus we get that the product of A and B, which is the product of the images of A prime and B prime, equals using our commuting square to the image of the product of A prime with B prime. And this is it belongs to the measure of the intersection. Okay, so this is maybe a heavy slide, but so if it was too much, don't worry, the rest is much easier. But this is the heart of the using of the relative symplectic cohomology of pairs in this tool of the ideal value quasi-measure. Questions? Can I move on? So, applications. First, so given a closed symplectic manifold and tau will be our quantum cohomology IVQM, we have the following important proposition, and it says that given two compact set with such that the product of their measure is not zero, then we cannot displace by sim zero the one from the other. For example, so on the left, the product is zero, and using sim zero, we can displace this set, but using ham we can't. And on the right, the product is not zero, and of course we can't displace the one from the other. And the proof of this proposition is quite short. So assume we can displace one from the other by phi. So phi phi of k intersection with k prime is the empty set, then phi of k with k prime commute and k prime commute. So by the quasi-multiplicativity, we get that the product of the measures is a subset of the measure of the intersection, which is the empty set. So using the normalization, this is 0. On the other hand, using invariance, we know that the measure of phi of k equals to the measure of k. Thus, we get a contradiction. Now we can use it and get new results. So for instance, on the 2n torus times S2 with a standard symplectic form, we take two equators of the sphere and define k and k prime to be an Lagrangian torus times an equator. Okay, for instance, the purple one and the red one. And what we proved is that we cannot displace using simp0 the one from the other. And the proof is just take product. Okay, so first just mention that using a smooth isotopy, we can displace the one from the other, and also using volume preserving isotopies, we can. And in the case of Ham non-displaceable, it was proven by Kawasaki using Lagrangian Frol cohomology. So we generalized his result. Okay, great. A question about it? Yes.
Can you explain some intuition for how you might have guessed that this would work besides computing?
How? Come again? How we got this computation?
No, would you be able to see that this would work in this case without just computing everything?
I don't know how we can see it without computation. I can't. Okay. Sorry, I have no good answer for that. Okay. Now, I said that IVQM is a symplectic analog of IVM due to chromo. So let me define what is an IVM. So given a compact Hausdorff space and an algebra with all the assumptions, and a IVM is an assignment from open sets to graded ideal that satisfies actually the same axioms except of the multiplicativity that we omit the quasi-multiplicativity and we get a stronger axiom. We take a stronger axiom called multiplicativity, and we just omit the assumption of the commuting. So now for any two open sets, the product of their measure is a subset of the measure of the intersection. Here's examples very similar to our example. Just take Chef cohomology or singular cohomology with some change, but the same idea works. And what we can use this object, so given a metric y of covering dimension d, and mu will be a IVM, y should be compact, but we will be fine in more general situation. And also we can take an ideal. We assume that there is an ideal such that its d plus first power is not 0. Is the dimension of y. So what we proved, this is actually based on a proof of Karasov. He proved it in a very specific case and without the language of ideal valued measure. So we translate his result. So this is a version of Karasov theorem. And what we proved that there is a point y such that for any compact subset, if I is a subset of the measure, then Y0 is belongs to Z. So it means that if you have a subset Z and its measure contains Y, then it contains Y0. So Y0 is in the intersection of all the class of all the sets of this type. There is non-trivial intersection here. And what is the connection with ideal valued quasi-measure? We want to translate this result to the symplectic world, and to do that, I have to define the notion of involutive map. What is an involutive map? So given a symplectic manifold, involutive map to a smooth manifold is a smooth function with the property that the pullback on any to the smooth function of y give you two Poisson commuting functions. And examples, first, we have a map from Rn with Poisson commuting coordinate. And also, in the case of torus, we can take a projection from onto one of the Lagrangian submanifolds, which is also involving. And what it is, it helps us. So the key properties are the following. First, if you have any two open set, then their pre-image give you commuting sets. That is the first and immediate consequence of that is that if we have an IVQM on M, then its push forward is an IVM. Push forward, we take the tau of pre-image. So for any two sets in Y, their pre-image commute, then using the quasi-multiplicativity, we get that the push forward is multiplicative. Okay. Thus, we can apply the last theorem of Karasov and prove the following thing, that given a closed symplectic manifold and an algebra and an IVQM on this algebra, and any involutive map from Y where Y is of dimension D, and we can apply the abstract center point to the push forward of our IVQM. So this is an IVM, and the conclusion will be that given an ideal I with such that its D plus first power is not zero, then there is F has a fiber that intersects all the subset with the property that I is contained in their measure. Yes.
Do I have the correct intuition that if I take a smooth manifold, I look at its potential bundle, I have like the projection is involutive, and then the symplectic Centerpoint would be a zero section?
I have an example, but not of this kind. So I wanted to show another example. For this kind, we can think about it. I have no answer here right here. But let me show you an application of this for a new symplectic rigidity phenomenon. So on the 6 torus with standard coordinates, take A, B, and C be points in T2. Okay, and I will define a family of three coisotropic tori as follows. So the first one, T1 of A, will be the collection of all the sets with all the points, sorry, with Q1, Q2 equals A. Then we'll take T2 of B to be the set of all the points with P1, P3 equals B. And finally, T3 of C will be the set of all the points with P2, Q3 equals C. Then we'll take T of ABC to be the union. And what we proved is that given any involutive map from T6 times S2 into any surface, so given such a map, we know that there is a fiber that intersects all the subset of the form T of ABC times an equator. Okay, and how we can prove it? We show you the proof. So we put alpha, beta, and gamma to be the classes of the corresponding two forms. So for T1 of A, we take dq1 wedge dq2. For the second one, we take p1 dp3, and the same for this. What we showed in one of the previous slides is the measure of T1 of A equals to the ideal that is generated by alpha. The measure of T2 is generated by beta, the ideal that is generated by beta, and the measure of T3, sorry, is the ideal that is generated by gamma. Here is 3 and 2.
Sorry, what was y again? Y2 because
Like this,
y, like in the statement.
Y is any surface, any two-dimensional manifold.
In T6 process too.
No, Y is any, we have a map from T6 times S2 to a surface. To any surface. And the theorem said that such a map has a fiber that intersects all the subsets of this type. So by the monotonicity of ideal by the quasi-measure, we know that the measure of T ABC contains the union of these measures. But since this is an ideal, we know that it is actually contains the ideal that is generated by alpha, beta, and gamma. Like unit, if we denote it by I, the product of this ideal with the quantum cohomology of S2, we get that this is a subset of the measure of T ABC with an equator. Now we can apply the theorem for this I, since I third is not 0. And thus we get our theorem. Questions? Okay, great. And actually, the last topic for this talk is what's called virtual commuting. So in algebraic topology, we know that we have many examples of excisive couples. For instance, open sets or CW complexes of a CW complex, CW subcomplexes of a CW complex. But in the symplectic case, this is not the situation if we consider the analog of an excisive couple, which is commuting sets in this sense, but for our case, commuting set. So we can ask if it's possible to make two sets commute.
What is a commuting set?
Complex subset or commute if there are commuting functions such that your set are exactly the 0 sets of this function. And for open, we take the complement.
Okay, thank you.
Okay. So the question given two sets, can we make them commute or if they are commute up to symplectic cohomology? So we said that A and B virtually commute if there is a symplectic morphism. Phi said that A and phi of B commute. This is a new definition, so I think this is the first time I show it for an audience. And let me give you an example. So first example, two disks in sphere. Any pair of two disks give you the disks commute, virtually commute. Since if you have a large disk and a small one, we can put the small one into the larger. Maybe we can make them disjoint, or in the case that both of the disks have an area half, we can make them to be a cover of the sphere, and then they are commute. Okay, and we proved a proposition, and the proof is elementary, not something which is really hard. Few sentences, and the proposition said the following: given closed symplectic manifold and a compact subset of M, and also we have an isotropic closed connected submanifold L, then we know that if L and K commute, then there are two options. First, that they are disjoint, and the second is that L is a subset of K. And let me give you an example of the case of non-virtually commuting. And the first example uses all this proposition and topological stuff. So given two orthogonal meridians in the torus, we know that their intersection product is not zero. Then we can't displace the one from the other. In general, we can displace the one from the other using any homotopy, not just simply homomorphisms. Any isotopy of continuous of homomorphisms. And also, since the image in the first homology of L into the homology of T is not a subset of the image in the first homology of K into the manifold, we get that there are no continuous isotopy, and in particular a symplectic isotopy that sends L into K. So by the proposition, we get that K and L do not virtually commute. So here we use only topological observation, but we can, in more complicated cases, we have to use more hard tools. So another example is in the case of T to N times an equator. So here also we have our previous Lagrangians. So a point times a Lagrangian times another Lagrangian, which is the equator, and this is A, and B will be its brother, the second one. Then I said that A and B do not commute, and I use actually the same argument, but now in order to prove that we can displace the one from the other, we have to use ABQMs. So we used our previous result and show that we can displace the one from the other by Simp0L. And the argument of the image of the homology is the same, like before. And since B is a Lagrangian, connected and closed, in particular is an isotropic connected Lagrangian, is a Lagrangian connected, closed, and isotropic. Our position said that A and B cannot. I think I finished the talk 10 minutes before. So thank you very much.
I ask a question which I'm not sure makes sense.
Okay.
It's rather a philosophical question. Like, so you said one of your main theorems, there exists this IVQM, and then in all your application, I have the impression it's you checking whether the product or something is equal to 0 or not.
Mhm.
But you have something in values in an algebra. Could you use more information, like more subtle, say, no, I have those two measure that maybe have take value in two different ideals? Then can you say something?
Into different ideas, maybe that what we can say. In this case, I think that we can prove that you can't move the one into the other, since if you can, then there were an inclusion of the ideas. I think that you can do.
Why does it call them a measure? Can you do
si-
integrals of functions?
Okay, so what it called measure, because of the axioms, and they are similar to axioms of measure. I didn't wrote here additivity, but it satisfies kind of additivity that said that if you have two disjoint open set, then the measure of the union equals to the sum, not direct sum, just sum of the measures. But we didn't use it at all in our project, just
But your measure also satisfies this. So can you define the integral of a function?
so there, we thought about to get a definition of kind of an integral, but we didn't really try to do it in serious way, and we didn't find any application of it. But we thought about it when we thought about connection with quasi-states, since quasi-states is kind of an integral with respect to a quasi-measure or topological measure. So we, in our mind, we thought about connections between these two objects, and actually there are connections, since soon Mack and Varolgunes proved that subset with non-empty measure in this sense is heavy. So there is a connection to quasi-states, to anti-Polterovich quasi-states. And also, when we try to talk about all of this stuff of relative symplectic cohomology, we wonder, we would like to prove what's called simplicity conjecture on quasi-states. And they said that any Frol homological quasi-state is simple. It was conjectured by Polterovich, and actually in the first version of Maxwell and Varolgunes paper from 2023, they wrote a proposition that from it's really easy to deduce the simplicity conjecture, and we saw it and write them, and they edited to the paper. Yes.
So in the definition of quasi-measure, is there like what's the condition if you have three sets? Is it just still product?
No, there no way. We tried, and we didn't find any way to make it for three sets. But
The quantum cohomology algebra has interesting multiplication. If you have three,
and it's a very interesting direction to think about it, to define a more general product with three inputs. We didn't try to do it. It's a good question.